Chapter 13, Universal Gravitation. We're going to talk about gravity, and obviously when we talk about gravity, we talk about Isaac Newton. But just so you understand, Isaac Newton did not discover gravity. They knew about gravity for quite a while. What Isaac Newton did was come up with the idea that everything had gravity, like the apple has gravity also. Okay, so I mean, back in Newton's time, we knew about inertia. Galileo was there, had been there, and come up with inertia. We knew about that. We knew that without this outside force acting on something, the object's going to go in a straight line. We know that if an object undergoes a change in speed or direction, we've got to have a force. So we know all this stuff at this point, But, what happened was, and this is probably more myth than anything else, but, the idea is he was sitting under the apple tree, he sees the apple fall, but really the biggest key is he's thinking about the moon. That's the big thing that Newton came up with in his law of gravitation. It wasn't so much about, hey, the apple's going to fall, it's going to go to the ground. We all knew that. They all knew that before then. What he's coming up with is, why does the moon not fall into the earth? Okay, so he saw it. Maybe he looked through the branches and saw the moon, whatever, But at this point, it says he was probably puzzled by the fact that the moon didn't follow a straight line, but instead it goes around in a circle. We know that if something goes in a circle, we have acceleration. If we have acceleration, we've got to have a force. Well, what is that force? Well, that force must have been gravity. Okay? So Newton comes up with the idea that, the moon must be falling around the earth also. So that's kind of the key point here as we're going through this. Because you know what? If the moon didn't fall, hey, it'd take off and go in a straight line. So it's got to be continually falling around the earth. And, it says that the moon falls in the sense that it falls beneath the straight line it would follow if there weren't any force acting on it. In other words, the moon, hey, it wants to go this way, but it really ends up down here. It falls that much, whatever that is. This is the force of gravity here, causing that to move, for the moon to change. So here we go. We've got our picture, Otherwise it's going to go off and keep on going. It's going to disappear. Not going to happen. So he kind of comes up with the idea of, hey, let's say I have a cannonball, and I fire this cannonball, not very fast, it falls down. A little faster, goes a little farther, and so on, goes a little farther, goes a little farther. If I fire it fast enough, guess what? It stays in orbit, because it is falling down the same distance that the Earth is curving down. So that's the idea of a satellite. So this is kind of one of his drawings, and his idea is that, well, if we could do that with a cannonball, same thing is true with the moon. It must be falling also. So that's kind of the big thing. And in here they talk about this tangential velocity. In other words, this is the speed it has. If we didn't have the curve, that would be the speed it's going. This would be its, right here, its tangential velocity. In other words, it's tangent to the circle, that this thing is going around in, and therefore that would be my speed if there weren't any gravity pulling it sideways or pulling it off the mark of where it's trying to go. Okay, so Newton's idea is that, hey, if the mass of the moon should not affect how it falls, we don't care about the mass of the moon. We don't care about anything else. We just know that it's going to fall. And so he can kind of calculate that by knowing, how far the moon was away from the Earth's center. And they kind of knew that at this point. So at this point, they know that the moon is 60 times farther from the Earth than the apple was. Now remember, we're talking about the center of the Earth. So here's my apple tree. You know, this distance here, you know, if that was x, you know, to the moon, this distance would be 60 times that. That's what they're trying to say. Now, they know that much. They don't know exactly how far it is, but they kind of have that general idea figured out. Now, what Newton says is, you know what? The pull of gravity here on that apple is probably stronger than the pull on the moon. In fact, since it's 60 times farther away, that force of gravity is going to be diluted not by 1/60th, but by 1/60th times 1/60th. And we'll get into why that is in a little while later. But basically he comes out with, and he finds out that the Earth should fall about 1.4 millimeters every second. So right now, in 1 second, the Earth has fallen a distance of 1.4 millimeters, traveled probably a whole much farther than that, but it's fallen towards the Earth that far. That's how far it would have to fall every second in order to stay in orbit, okay? So, since it's 60 times farther, this is our picture, 60 times farther here, it's going to have farther to, you know, it's going to have not as much force, and so on. All right. So Newton calculates how far the circle of the moon's orbit lies below the straight line, comes out with this 1.4 millimeter distance. Pretty amazing when you think about it, because at this time, you got to understand, they don't have all the fancy equipment that we have. They can't measure things exactly. They can't do all that. He's doing most of this using thought experiments, using calculations, you know, and stuff. They don't have the exact Earth-Moon distance, but yet he still came out with this number, which is pretty close to the right number that we accept today for what happens. Okay, so that's pretty good. I think that's pretty impressive for a guy in the 17th century or whatever it was. Okay, so you know we kind of talked about this quite a few times. He does eventually publish this, but not until after he comes up with what you guys' favorite thing, calculus. Okay, so calculus allows him to do a little bit more. You know, and at this point, remember, you know, all this stuff was done before they knew all calculus, and he kind of comes up with all that. So, some pretty good thing. Probably, I think most people recognize Newton as being one of the, if not the most important scientist of the, you know, of Earth history, I guess, basically would be one way to say that. Okay, so let's keep going here. All right, so at this point, obviously, we know the Earth's no longer the center of the universe. You know, not only is the moon going around the Earth, but the Earth is also falling around the sun. We've got the gravity of the sun pulling the Earth around in this continual velocity, you know, this continual path that we have there. So, it says, what would happen if the tangential velocities of the planets were reduced to zero? Well, let's go back here a second. If all of a sudden we had none of this here, well, what's going to happen? Yeah, we're going to head straight towards there. It's going to be a little warm. Okay, might need to turn the air conditioning up a little bit. Would not be a great thing. All right, let's talk about the law of universal gravitation. What Newton comes up with, he figures out that if we're talking about the force of gravity, it depends on a couple things. It does depend on the masses of the objects, so whatever those two masses are. And it also depends on the distance, but the distance squared. So as we're, you know, if we double the distance, we only have 1/4 the amount of force that is there. Okay, so that's his. He comes up with this proportion. It's not yet a formula yet because we can't quite get it there yet, but we do know that the farther apart we are, you know, if you double the distance 4 times, it's 1/4 as strong. If you triple the distance, it's going to be 1/3 as strong. So if you're up on top of a mountain, you know, you weigh less for one simple reason. You are now farther from the Earth's gravity than that person who is standing in the valley. So the farther you are away from the center of gravity of the other object, the less force there is going to be upon you. So eventually, we've got this formula. If we know this constant, this is known as the gravitational constant. If we know this gravitational constant, we can come up with the exact amount of force that is available. Now, this is not something that Newton came up with. He did not come up with the gravitational constant. He just came up with the idea that force is proportional to the masses divided by the distance squared and so on. So we'll talk a little bit more about how they come up with G. The idea, the value of G, if we put in numbers for this, we come up with the value of G of being, 0.00000000000667 newtons, or how about this, 6.67 times 10 to the negative 11 newtons, meters squared, kilograms squared. Once again, this is one of those constants, so the the labels are always weird, but it's so that the labels will cancel, and eventually this is the constant if we want it in newtons. If we were doing it in pounds, it'd be a different constant, but since we're in physics, we're going to do everything in the SI system. The first guy who ever did this came up with G is a guy named Henry Cavendish, and he kind of an interesting way that he figured this out. But this is now 150 years after Newton's idea of gravitation, so we're coming out here a long ways away, and Cavendish comes up with it. Another guy named Philip van Jolly also figures out a way to do it. It says, attach a spherical flask of mercury to one arm of a sensitive balance, then rolls a 6-ton lead sphere beneath the mercury flask and figures out how much the balance is being pulled down, and from that can calculate this. So here's a picture of what it is. So he's got his mercury in here, back when we didn't know mercury is such bad stuff probably, so he's probably playing around with it. We've got this big 6-ton sphere, got a real sensitive balance, probably not quite what we see here. But then they measure exactly how much force, so they get it balanced, and then they roll this rock, this big thing underneath it, and they do it. Now, this was probably, some university somewhere, and I can just imagine him going to, the person in charge of the money, hey, I need to go buy this big 6-ton rock so that I can stick it under my mercury and see how much it's going to pull down on the mercury. I just wonder how, you would fill out a purchase order for something like that. Anyway, what we do find out is that gravity is very, very weak. We know of 4 forces in the universe, and gravity is extremely weak. It is by far the weakest one. And the others aren't even, they're massively bigger than this one. But the interesting thing about gravity is it is over universal, over long distances. It can work over a very, very long distance. Okay, so Cavendish, we talked about Cavendish being like the first one. This is probably, they don't really talk about this, so I assume this is a little more complicated method of weighing it. But this is interesting. When he comes out with all this, they really said that what he was trying to come up with was the mass of the Earth. This was, or they called it weighing the Earth, because once we knew what G was, we could then put in the information and come out with the Earth. Remember, so here's our formula, F equals G times M1, M2 over distance squared. If we take like a 1 kilogram mass and we put that in, we know 1 kilogram. We don't know the mass, that'd be my mass of the Earth. We know the distance, whatever that was. I think it's Earth's radius 6.4 times 10 to the 6th, 10 to the 6th, and you'd have to square that. And so once we know this number, this 6.67 times 10 to the negative 11, I didn't leave enough space here, we know that 1 kilogram is going to give us a force of 10 newtons. The only variable left is the mass of the Earth. So once they calculated this, up to this point, remember this is 150 years after Newton, but once they calculated that G, they could now calculate the mass of the Earth. This was a big thing. This is a big deal. So, newspaper, hey, scientists measure the mass of the Earth. Obviously, it's pretty tough to go put the Earth on a scale. So this was how they first came up with. So if you ever wonder how they would know the mass of the Earth, that's how.